Great. All right. So I guess we can start with the town hall and let's go through the agenda. So as you all know that we have just closed round one, and hopefully there is a bit of testing going on in the background. So hopefully by the end of this town hall, round two will be up and running. We already have an updated starter kit for round two, and you'll be able to access it after the town hall ends. But yeah, so that's one of the reasons for you to stick around till the end of the town hall, apart from an excellent guest speakers that we have. So first up, we will try to understand, this is a very unique challenge, right? And we'll try to understand why this challenge matters, what is the motivation behind it, and Frederic will be the one to walk us through it. Then we'll try to understand the challenges in digital entomology, and we have expert Roger over here to speak about that. And Monika will be walking us through the problem statement and the data sets and the baselines that already exist. John will walk us through the current solution, some of the highlights from round one, and also what to expect for round two. We are open to taking questions for each speaker in middle of their at the end of each of the talks. You can drop them in the chat. You can raise your hand, unmute at the end of the presentation. But we also have a dedicated Q&A session at the very end for general questions that you might have across the spectrum. And then we'll have a quick feedback session for to understand your experience from the first round. What would you like to see in the next round? If there are certain things that we can improve during the course of the remaining of the challenge. And that's the agenda for today. So let's kick off with our first speaker, Frederic Bartumeus. I mean, there is a description over here, a long description over here of everything that he has done, primarily his work on animal behavior and disease ecology. But I think maybe if he can kick off his speech with a short bio about himself, that would be best.
Well, yes, it's a pleasure to be here, and I'm super excited about this challenge. And yeah, basically my background is ecology, but so I used to use new technologies because I always think that ecology needs as much as other disciplines of biology, like biomedicine, for example, of new technologies, because we are facing a very exceptional situation at the global level with global warming, and there's many other droughts, many other ecological problems. One of them also like the growth of mosquito-borne diseases. And this is what I've been working on for the last 10, 15 years. And I think I can start right away, explaining a bit why all this challenge matters and what are the real questions that we have behind. So I will share my screen so you can listen to me fairly well, no?
Yes, your audio is great.
Okay. And now I'm going to share, let me see, view slideshow. Okay. So the first thing is, what is Mosquito Alert, no? And Mosquito Alert can be defined as, with these words, is a citizen-based early warning system for mosquito-borne diseases. And as you can see here, there's a set of keywords. The first one is the citizen-based. So this is a participative system where we are asking for information to citizens to build an early warning system, which is a system that would allow us to anticipate the invasion, because many of these mosquitoes that we're tackling are invasive mosquitoes in Europe. This is mainly focusing in Europe, but the pan-European view. But as you will see, we can extend these systems all over the world. And indeed, we have collaborations with other people in the American continent, for example. And also we are starting to do some projects in Southeast Asia. And the other keywords are mosquito-borne diseases. No? So mosquitoes are insects. You will know a bit more in the next talk about them. And they have complex cycles, and they bite humans, and in that bite, they can transmit diseases. Mainly, we're talking about viruses like dengue, chikungunya, Zika, and others. And our idea is that with the help of citizens, as it's very complicated to understand the dynamics these insects populations. It is that trapping, to make trapping efforts, which is what entomologists do to cope with to try to understand how they are distributed and what is the dynamics. We thought that having information on images would be really useful to complement the traditional ways that entomologists use, to know about these species. And that's the basic idea. Then you will see that all this is a challenge, and we'll explain a bit more about the insights of Mosquito Alert in the next slides. But just to follow on what I was saying, CitizenScience plus digital tools, basically smartphones, were seen like this. We're talking about almost 10 years ago, as an opportunity for mosquito surveillance. And citizens can be really interesting and important sensors because they know about mosquitoes and they can tell us many things about them. When they have been bitten, where they can make pictures of the mosquitoes. Of course, they can submit us texts with feelings and information that can be relevant for us. And at the same time, this idea of communicating with citizens allows us also to encourage people to collect information, but also to raise awareness about the problems that mosquitoes are carrying, which many of the normal citizens don't know. And they don't know, for example, they, without them knowing, can breed mosquitoes nearby their homes. So there's, can you hear me well? So I see my connection is unstable. So there's a number of reasons. Okay, there's a number of reasons why Scala, we think that this is a useful tool. There's, of course, scalability, the problem of scalability, the problem of mapping mosquitoes at different scales, given that these are insects and the dynamics is super fast, but also other things like trying to cope with information that is real time, which for public health authorities is very important. And the idea of, having this information in a flexible manner. So it's easy once the system is built to collect information, order it, prioritize, filter, and provide this information to what we call stakeholders, which is the people that might be relevant in terms of using that information for the good of citizens. So this is also an app, and we are targeting 5 species of mosquitoes that are of concern in Europe. But as I was telling you, we are going to be probably extending this number of species to other species that are also relevant in other parts of the world. We also collect information about bites. And so just a brief on that. So it's different to try to get estimates of population abundance and population dynamics of mosquitoes when they are biting. So of course, abundance and number of bites is correlated, but sometimes it's not exactly the same. And the bite information provides us much more tight information about the human and mosquito interaction. We also collect information about their life, that they live in the water, they are larvae, and this is a very important moment of their life where we can do actions to control for the populations. So mapping these breeding sites is also important. We can ask people to collect samples of mosquitoes and send them to us so that we can do some molecular analysis as well. And very important, we can communicate directly with citizens. All the system is anonymized, so we don't know who is who. We don't ask for, Facebook accounts or names of people, emails. We don't know anything, but we have devices, UUIDs, and we can communicate with them if we see that they are sending us, for example, nice pictures or pictures of a relevant mosquito. We are also tracking people, but in an anonymized way. We use this background tracking to then have estimates of the sampling effort. It's like if we would be putting traps in the landscape, but instead of traps, we are releasing citizens that are aware of the problem and are willing to participate. And it's very important for us when we do models to get to know the biases in this sampling effort. So all in all, this is the main thing, the app. But as you can imagine, we call Mosquito Alert a system. It's an ecosystem, real, where aside from the app, which is the bottleneck where we collect information, there's many other things going on. There's a digital entomological lab with experts validating the pictures. This is how we build up the data set that we're giving to you. We have stakeholders trying to use this information to control the populations of mosquitoes. All the information flows to different data servers. We have a nice API that we are sharing. Everything is open. We have a map. We generate the raw data in the map so that people can get the data already from the map directly or from other servers of data servers. And we have scientists doing science and doing models out of this data. So it's a whole bunch of things that involve this Mosquito Alert ecosystem. And not only we do have science behind the data and scientists, but we also have these experts, entomological experts, that is a super important network that we have been building up with the years. We started in Spain, but then we expanded it to all over Europe. And now we have what we call 24 national supervisors. So there's people leading this system in each of these 24 different countries. And then we have about 100 experts validating these pictures. They help us also in other tasks, like translating the app to different languages, disseminate the project in their countries, and give feedback to participants as well. This is just a video of the evolution of the participation in Mosquito Alert over the years. And the last years after the COVID pandemics, we had a huge surge of participation because we enter with strength in different countries like Netherlands, Italy, Hungary, and not only Spain. Through the projects, European projects that we are participating in, and one of the projects is the VIO project, which is the one that is allowing us to generate this challenge. A bit of statistics. We are not still on big data scales. This is rich data. We are talking about hundreds or tens of thousands of reports. But the spatial coverage is starting to be nice. The more we go, the more data we have, and there's nothing but growing and growing about this system. This is a visualization of the invasive process of one of the species that we're looking at, which is the tiger mosquito in Spain. And this map is a combination of traditional source data, the standard trapping data, which is slow, is costly, and not really effective in time, and our CitizenScience data with Mosquito Alert. As you can see, from 2014 onwards, we really increased the number of municipalities where we were detecting this mosquito, thanks to this system. In April 2023, so this year, for the first time in the national surveillance plan for these invasive species, the Ministry of Health included Mosquito Alert as a surveillance tool. So that means that now this surveillance tool is promoted in Spain in all the regions as a combination with the traditional measures that the Ministry of Health is imposing to these different regions, in order to control for these insects. We are trying to do not just having these maps at the time that these images are coming up, but trying to be as fast as possible. And I want to explain the details of this flow of images that this diagram that is here. But the idea is that we have a standard flow where the image goes into the system, and there's three experts that validate and give their opinion on the image. But this, we realized it was not fast enough, because you depend a lot on these entomologists, and they have other work to do, and maybe they are not attending the system as rapid as we would like. So we were, of course, in the need of introducing artificial intelligence, because aside from having the human expert side, we need machines that are faster, and we need to train these machines to provide classification as fast as possible, that then can be also validated by experts, So our idea is to build up this socio-technological system where we have human experts involved, but we also have machines and artificial intelligence involved to try to be as fast as possible. This is how we start with our artificial intelligence algorithms in the system, and this is where the challenge was key and important, to see whether we can improve what we were having and what we were doing, and see what new solutions you can propose. And this classification in the future, and currently now we are already testing it, is going to be combined also with geoposition data, such that when we see an insect of a given species in a given region where we know it should not be, we can trigger an alert very rapidly with a given amount of accuracy. And we can send, for example, an email to specific stakeholders in the region for them to go to the field and test whether this species is there, or for them to contact some of the citizens that have been sending these images. This is what we are really meaning by an early warning system. On the top of that, we're doing science, we're doing modeling of this data. This is biased data because participation is biased, but we can control for this bias. And for example, in the city of Barcelona, where we are more or less settled, and so there's a lot of data there since the very early times. So we are now currently building up real-time models on a daily scale resolution and 20-meter resolution, where we're using the CitizenScience data combined with weather data and other socioeconomic data about humans to make a map of the risk. For example, in this case, I'm showing the risk of having tiger mosquitoes in Barcelona over a season, over a year. You can see it's 2 peaks. So tiger mosquitoes usually peak 2 times, one in July, another in September, but you also can see where the mosquito is spread in space. So not only we can do this at the city scale, but also we can do that at other scales. And I invite you to go to the Mosquito Alert webpage, look at the map, and then go to these other visualizations that we have, where we are showing presence absence data provided by the citizens in different colors, whether it's in the known distribution of the species or it's outside the distribution. And also we are generating probability models that give you the likelihood of having these insects all over Europe. And I'm finished. So I let the floor to the next speaker, or if you have one question maybe or two, I can try to answer.
Yeah, I guess we can have floor open to a couple of questions. Once again, if you're feeling shy, if you don't want to unmute, you can drop your questions in the chat box. We'll also have a dedicated Q&A session after all the speakers are done with the presentation. So that's also an opportunity for you to ask your question. But if we don't have any more questions, I guess we can move on to the next speaker. Okay, I guess we can move on to Roger's presentation, who is an expert in mosquito research and control, and his work mainly focuses on ecology of invasive species and how they interact with humans. And he also has been developing sustainable control methodologies to deal with the same. So yeah, I guess we can.
Thank you very much, Diana. Okay. Good day, everyone. I'm very happy to be here, mostly because, we are very specialized people in entomology, and we are always meeting each together, and we are chatting about our strange things. We are quite freaky from a general point of view, and we don't have so many occasions that we can chat and to explain what we are doing and what this kind of strange things we do with insects, or how we study them. So that I'm very glad to be able to show you some of our inner world, what's closer to the mosquitoes. Some basic info. Mosquitoes belong to the family Culicidae, true mosquitoes, despite people may call mosquito as many other things, but there are less than 4,000 species. of mosquitoes, and they all share that the immature stage are aquatic. So if there's no water, you don't have any mosquito. It's as simple as that. Larvae are not recognizable as future mosquitoes because they are like worms and they are very characteristic, but they don't look as mosquitoes actually. And that most species of mosquito, not to say all, are blood feeding. That's what makes their most annoying characters. Mosquitoes are very nice subjects for citizen science because motivation is granted. As you know, mosquitoes are really annoying, and that makes them a very social subject. They are community issue most of the times, and they are a lot of cultural assets. Public health concern is also high because some species in some situations can transmit really serious diseases to humans and to animals as well. And also that a citizen science do not need to be freaky of butterflies to see something, to have to look for butterflies. Mosquitoes are looking for us. So they came to us, don't need to be very involved to chase mosquitoes. They chase us actually. So what's important to differentiate mosquito species? Actually, they have specific abilities to transmit diseases. Only some species can transmit some diseases. Not all of them do. And additionally, there is a very strong ecological differentiation between species. Not only in the kind of blood they are looking for, many are taking blood from humans, but many other are biting frogs or reptiles or just birds. So that's important. But they are also specialized in the kind of water they are using to breed, because a control of a specific insect or a species of mosquito has to take into account where the larvae are found, because commercial and public mosquito control is always focused to the larval stage. So that it's very different if you have a marshland mosquito than if you have a tree-hole breeder mosquito that is breeding its larvae in the trunk of the trees in small holes that have water inside. So for education people is also very important to have differentiation of the mosquitoes, and some mosquito species are invasive, by the way. So which are mostly the ones that we are focusing to. As the life cycle of mosquito very shortly explained, these are the eggs. These are eggs of Aedes albopictus, and they are very highly enlargement because it is taken with a microscope. They have less than half a millimeter each. When they hatch, they give these are larvae. These are very fast living, and only 4 days they can reach to the pupal stage. Usually they do that in the case with the species we are tracking, especially, and most of important it's Aedes albopictus, and they do that here, just at home of the home owners, and place at your place in the very small recipients where you may have tens of thousands of larvae. When they are mature, larvae will turn up to pupae. This is a place where metamorphosis will occur, and when that process is over, then the real mosquito will emerge to the surface. This is the time where people can start to acknowledge they have mosquitoes breeding at house, because this is the moment when they became recognizable by citizens. It's important to state also for your work and for your interests that there is sexual dimorphism in mosquitoes. You have here the male is at the left and female is at the right side of the screen. There are some differences which are not very obvious at the beginning, but mostly males have much more feathery antennas, and they have very long maxillary pulps. Their proboscis is not biting because only females can bite. Females have much simpler antennas and a biting proboscis and short maxillary pulps. Males are not very often photographed by citizens because they are short-lived. Their only function was sexual. This is the mating of the female and the male, and then they die. So they are not very well spread around. Most of pictures we are going to see will be females. After mating, females get inseminated per life. They keep sperm of the males in the special organ, and then they start the cycle, the gonotrophic cycle, as it's called, that taking blood meal and laying a batch of eggs, because mosquitoes, only females are biting. It's not like other blood-sucking insects like fleas or lice, where both sexes are taking blood. In mosquitoes, only females are taking blood, and only in that specific moment of their lifetime. The rest of the time, they are sucking just on vegetables. They are taking carbohydrates from vegetables. Then the female takes our blood and turns it to eggs. That's as simple as that. And the whole process may take as short as 10 to 12 days in summer, depends on the temperature, of course, and the host availability. And every cycle allows the female to lay up to 150 or even 2,200 eggs per blood male. That makes for a huge potential reproductive for these insects, which is normal because they are opportunistic insects that use temporary borders, and they have a very, very high demographic strategy. Okay, now we have seen the main aspects of the cell life cycle. Let's shift to our things. It's like we have seen how the mosquitoes live, and we have known that we have the need for identifying a species, of course, and then the next question is, how do we do that? Up to now, the entomologists were just chasing mosquitoes in the field, and they still do, of course. We do, actually, because I've spent almost 40 years chasing mosquitoes in the field, taking them to the lab, and then identifying two species. That's made in the case of larvae. As you can see, we have very complete maps of features that are found either in the thorax, the head, or the abdomen of the larvae, which is at the left side of your screen, or in the bottom up of the body, which is a siphon, which is a respiratory organ, because they are breathing oxygen from the atmosphere. They have not bronchi. They are this kind of organ, which is a respiratory organ, which siphon, and has a number of characteristic features, like this siphonal tuft, combs, scales, and morphology, which are, as you can see, they are all numbered. And they are numbered, codified, and recorded for each mosquito species, and which are allowing to discriminate between the species, as we will see later in a very basic way. As a side note, this is more maybe on a funny side, we can identify also males, adult males, but this is quite complex because you need to prepare the genitals. So you have to dissect male genitals, you have to boil them, to take them apart, and transparenting, fixing, and follow quite a complex process, and ends up with a mounting and examination in the microscope. And this is quite, this is not very common because it needs a lot of time and effort, but it's sometimes necessary for you that from the field are males. You have genitalia from Culex pipiens, a common house mosquito in the left, and one from Anopheles in the right. But this is like a interesting fact. We are interested in females, which are the stages and the individuals that people will tell us about, and they will provide data. Females are identified in the lab, of course, by morphometric morphology and by setae and tufts and colors and patches, as we will see, following also this kind of schemas. and using normally identification keys, which are dichotomic. So that means that it's like a tree structure, so that if you are going to undergoing a question, for instance, here you have number 9, and then the question is the pulps are pale at the apex. These are maxillary pulps. And then you have in the good case, we have also pictures, of course, or drawings, like in this case. So if you check the 6.158, which is this one, you can see, okay, I see this is the pale spot at the apex. Either it has or it has not. So in this case, it has this spot. Then you go to point number 10, which is the next one. But if it is not, you need to go to the point 11. And then once we are at point 10, because it had the white spots, then you have got more questions. Just in this case, maybe on whatever. In this case, with dark scales in the wings, we don't have a picture here because it was on the next page. And then you can ask more questions. And at the end, which is quite easy in this case, you already got to the species determination. So if you have all these characteristics together, then you have an Anopheles argenti. If and otherwise you have all these other characteristics pulled, then you have Anopheles superpictus. If you don't have any of these two situations and in your specimens, then it will mean that you messed up somewhere in the previous steps, and that you just decided to you made a bad decision. This is like like phylogenetic tree. It's just a tree-like process just to get to the final determination. There are more modern keys that are software keys that are interactive and they are assisted by images. In this kind of keys, like this one, which is Mosquito Falk from Schaffner and collaborators. And then you have all the available characters together, and you can choose which one of the characters you would like to start with. And then at any time you can get back. If you see that we are you have no good choice, we have not a good choice, you can get back. And at any time you have the potential species remaining here. And every time you are checking a given character, then you get in your screen pictures of the different options. That's quite nice because you have real examples and you can get back at any time. It's much more interactive. The last generation of identification and lab, of course, is genetic techniques, which in future they will probably be very, very widespread because you can use any part of the mosquito body and you get with existing libraries, you get a very, very precise identification. You need a lab, a specialized lab, but they are increasingly more common. Okay, so this is what we do in the lab, but we are using images. Our challenge is to use images to identify species. We cannot do genetics. We cannot go to high detail because we have what we got in our screen. These are probably the most nice or the prettiest mosquito species in the world, which is a sabetine, it's a sabethis from Amazonian in the left, and probably the ugliest one in the world, which is Culex pipiens at the right, and is actually the commonest one. And this mosquito has nothing. That's no characteristics no special characteristics to discriminate. What are we looking at as experts when we only get a picture of a mosquito? Well, there are some of macroscopic features that we don't need a microscope or a loop to check at, which are mostly the length and the color of maxillary pulps, the aspect of the scutum, which is the dorsal part of the thorax, knees. In any of the legs, you may hear there are very, very conspicuous white spots in the knees in this mosquito, which actually is Aedes geniculatus, which takes its name for these knees actually, because geniculus means knee in Latin. And we also check patterns of the abdomen, just like there were patterns in the thorax. Abdominal patterns are also useful to us, and also stripes or ornamentations in the legs. We need to take into account that anyway, that most of these things, of these white patches that are so prettily seen in this individual, this is a newborn mosquito, so it's a very, very nice condition. But all these kind of white ornamentations are usually made by white scales that are easily lost, just like old butterflies lose their scales in their wings. So that you need to take into account that sometimes you don't see something, but it's not because it wasn't there, it's because it isn't anymore, but it was. So that's an additional difficulty. We have to evaluate how old the insect is and what could have it lost. For the thorax, for instance, we have everyone is building just fact sheets and reminders like this one. These are all the thoraxes from the mosquitoes of the genus Aedes in Europe. So even invasives like Japonicus or Albopictus. So using these kind of things, they may seem very similar to many of you because lack of experience, but it's actually quite straightforward in many cases. For instance, Aedes albopictus has a diagnostic white line. Aedes vittatus is very nice because it has 6 dots, just 6 dots in the black thorax. And this way you can get to a first approach of which species could it be. There are a number of fact sheets of this kind. This is for one from ECDC. This one is just restricted to invasive species in Europe, to the 6 species we have. This is Aedes aegypti, Aedes albopictus, which is a tiger mosquito, Aedes atropalpus, which is not very, very relevant because it has not spread much. But we have also Aedes japonicus and coraicus, which we will be talking later, and Aedes triseriatus. And here, ECDC provided this kind of fact sheet just to allow people to, mostly not very experienced people or people that are only working on pictures, which kind of things to look to just to assess species probability. As we don't have the individual, we need to work always on the probability concept. So we are on not. It's very severe, but not frequent that we can do this species 100% security. We are like artificial intelligence in this case. We need to always state the level of certainty we have about our advice. In case of albopictus, for instance, a few traits that you can see in this kind of pictures are diagnostic, like this white line in albopictus. So we have a mosquito that has a white line and has on the last segment of the leg white. You can be sure 100% this is albopictus, even if it's only a picture, because these are unique characters and they are not easy to mismatch with anything else. But this is not the rule. This is not normal. This is not a general rule. In general, we can get to the genus level. Perhaps we cannot say it's Aedes triseriatus, but we can quite easily say, well, this is an Aedes because of general characteristics of iodines that are quite easy to observe. But the species level is more difficult. So we can only guess. And then we have another problem, which are the subspecies level, which is the case which I will explain now finally, because this is one of the things we are dealing with in Mosquito Alert in Europe at this time, which is the complex of species that are very similar, that are invasive in Europe, and they have very relevant, but have different distributions. So we are going to discuss the problem of the possible confusions between Aedes japonicus. These are species actually that you have in the training set of the challenge. we have Aedes japonicus to differentiate from Aedes coraicus in a general layout of the problem. But this is made worse because Aedes coraicus has introduced in Europe with two subspecies. The mainland form, the continental form, which is found in the continental Korea, but also the form of Aedes coraicus, which originates from the island of Jeju-do in southern Korea. So we will see now what are the tiny morphological differences, just to allow you to checking what kind of challenge we have now with this species. Let me pinpoint that in the system, we are only trying to separate Japonicus versus Coraicus. We are not dealing with Coraicus. That subspecies of Coraicus, that's too much. We are only interested in Japonicus versus Coraicus. These are illustrations from our system. And then you can check here that the main differences between Coraicus and Japonicus is that lateral golden lines in the thorax that are quite short in Coraicus and are longer in Japonicus. But there's an individual variation additional. So that's happened very, very, very frequently, that you have individual variations between populations or between samples. And also you may have a real Japonicus, but that has ripped off many scales because it's an old female, and it looks like the lines are short. You better rely on the third leg, not the first, not the second, but the hind leg, because Japonicus has 1, 2, 3 white rings in the legs, and this part, which is the latest tarsomeres, are not have not any ring, whereas in Coraicus they have 1 or 2 rings. 2 rings in this case because this is a form from Jeju-do. So there are other characters. We will summarize just to end up with this. There are others. This is from a reference publication or Japonicus and Coraicus. As you can see, things that allow to separate Japonicus from Coraicus are absolutely impossible to check in a picture. You have Coraicus on the left. Oh, this is Coraicus, this is Japonicus. So you have Coraicus, you have these white patches, this white patch of scales in the metameron, and here it isn't. You don't have it in Japonicus. Additionally, to some city in this area, in the prespiracular area, which are not even seen in this picture, honestly. And then Japonicus has a very narrow, dark ring in the base of the femur, which is not visible in any picture by any chance, actually neither. And then you have the third leg. Third leg can be, you can see the differences because this is Coraicus mainland form, has this ring, whereas Japonicus hasn't it. To summarize, these are the 3 insects. We have Aedes japonicus with 1, 2, 3 rings. We have Aedes coraicus mainland with 1, 2, 3, 4 rings. And you have Aedes coraicus from the Jeju-do Islands with 1, 2, 3, 4, 5 rings. So I insist we are only trying to distinguish Japonicus from all Coraicus, but it's quite difficult as a challenge because most specimens have lost their legs when they are photographed, or just people are taking them to take the picture by the legs, and they are hiding as the character that would be more useful to identify them. So to deal with that in the system, we just boiled an additional category, which is a complex. So if our human experts are not sure about this is Japonicus or this is a Coraicus, they can classify the specimen or the picture, the report, actually, the citizen report, by a complex Japonicus.Coraicus. So in this case, they can be sure it's one of the 2 species because they are quite characteristic species, both together. The golden lines, for instance, are unique, but they cannot distinguish which one is the species. And it would be very relevant to make that difference because they have different ecological niches. They have different dispersion patches within Europe. Not that they are transmitting diseases, happily, but they are in different places and different locations. So it would be very nice to be able to distinguish them. And that's one of the topics that we are expecting about your work and future developments and future trainings of the machines to be able to separate these two species. And that's all from my side. Thank you very much for your attention as well. And if you have any question, I'm here now or at the end of the session.
Thank you so much for your presentation. I learned a lot about mosquitoes. I had no idea that only females were the ones who bite. But yeah, there was a lot of interesting information over there. And I'm sure that it will translate in helping people develop better solutions for this challenge as well, getting to know the species more, getting to know beyond just looking at images and the classes that we see in the dataset description. So if anyone has questions for Roger, please drop it in the chat or unmute yourself. You can ask the question, or we can move on to our next speaker, and we have a Q&A session at the end. So we can discuss the questions then itself. Okay, I guess we can move on to the next speaker, Monika, who is an expert in web development and AI. And she's really passionate about using AI for social good. And that's the focus of this challenge as well. So we'll learn more about the details of the challenge, the problem statement, data set, and baselines from her.
Hello, everybody. Can you hear me well?
Yes, we can hear you and we can see you well.
I would like to talk more about the technical details and explain you a bit, which you probably already know, why we decided to host that challenge. Basically, two reasons. First of the reason, as you already seen from Frederic and Roger's presentation, this is a complex problem we're dealing with. And we thought the great idea would be like a brainstorm solution. So we probably haven't thought about everything, and participants can give us great insights, checking the data, giving us their ideas, and we can benefit from that. Other than that, whoever starts to learn machine learning and computer vision probably get to the same problem I get when I was starting, the lack of the data sets and the real data set. Whenever you train your model on something which is especially prepared, you have great results. But later you try to work on real problems and your model doesn't work well because the data, it is not what you expect it to be. And that data set from Mosquito Alert, I think, is a great tool for people to work on a real problem with a real data, with complex issues. And that is basically why we decided to make that challenge. So we can get the insight from the participants, but also participants can, those who are starting, they can learn. Those who are already advanced, they can see something, how complex is, for example, that mosquito identification, because I didn't know when I started Mosquito Alert project as well, that tiny differences between the species, which even experienced entomologists, they have to dig into the images, check it. It is not as easy as distinguish dogs and cats or any other problematics. Here we will talk a bit about the challenge timeline. It is already started in the 20th of June. We finished the phase 1, and now we will be launching phase 2 really shortly. The phase 2 will be a bit different because now we expect participants to show us the solution. The first one was that we were expecting only to give the CSV file, which was evaluated. And now we would like to see what is the solution behind it. The winner announcement will be on 10th of November, 2023. And the challenge prizes, the first place will be the travel grant and the conference access, and the Apple MacBook Pro. The second place, it is the conference travel grant and conference access. And also the third place, it is the travel grant and conference access. And there will be really interesting conference, applied machine learning days. Whoever is into artificial intelligence, I think it's a great opportunity to learn something new and meet another people and meet the community. And coming back to the data set, to the problem, as you can see from Roger's presentation, the mosquitoes are just really tiny, and spotting the right features, it is really difficult, especially that whenever you try to make a photo with the mobile, it is not really easy to even zoom to make visible the legs, which the legs also carry the important information, the pattern. It is, and we thought that approach of small object detection can be useful. But like I said before, there's really small amount of data sets to even train the neural network in a small object detection. And we thought that this could be beneficial for the artificial intelligence community. The challenges, I'll just repeat a bit what Roger already said. Well, we try to distinguish something which is really, really small. And sometimes even if I try to make the photo myself, the mosquito, the legs of a mosquito, they become like a transparent to the image. So it's really hard to capture, even if you try from different angle, to capture all the features which you would like to be visible for the artificial intelligence or the human expert to recognize one species from the other. And our photo in the data set, this is the real photos. It is the photos which citizens take and send it by us. So they are different. Some of them are from experienced users who already know how to do the photos, how to spot that pattern in the thorax. And some of them are just from people who start taking photos and start participate. So it's a different quality of images and different quality of the photos taken. Like we already said, that correctly identifying a mosquito is a difficult task, even for the experts. And as you can see on the left, on the right, there is the image of the mosquito. It's really easier for us to use that citizen approach, because the traditional methods are very expensive and slow. That's why we're hoping in machine learning and deep learning techniques can speed up the process. And I will talk about the data set now. The first phase, which already finished, was a subset of the images which we have. It was 10,701 images with labels. It was divided in two subsets. 80% was a training set, which is 8,025 images, and 20% was used for test purposes, 2,676 images. All of those were used by mobile phone. And also the problematic is that the data set has a class imbalance, because most common species is most represented in the data set. For the phase 2, we prepare the new data set, and it's contained of the trained data set from phase 1 together with test data set of phase 1. So altogether there's like 10,357 images and labels. It will be available for the participants, and the participants can use it all for the training, or they can use it for training and test and divide it by themselves. For the privacy and data protection, all the EXIF information has been removed, and also geolocation has been removed. The ground truth, it is the ground truth created by our entomology expert, like Roger. And the example, it is in the image here, the class label, it is something which we get from our expert who were carefully looking at each picture and decided to which species it belongs. The class labels are used in the datasets above the same for the both phases. It is Egypti, Albopictus, Anopheles, Culex, Culiceta, and that complex Japonicus coraicus, which Roger was explaining us why it is that complex species. And for the participants, there was a prepared notebook with baseline, which you can try to use it yourself and create the CSV file with predictions. That baseline was done by training YOLO-V neural network from Ultralytics. There is a link for the training tutorial, and the parameters was the custom data. There was entire trained dataset from phase 1 used for the training. The weights were pre-trained on a COCO dataset, and the epochs was 100, the number of epochs. The hyperparameters were default. The Ultralytics has lots of different models of the neural network. We choose the size small, which is not the smallest because the smallest is nano, but this one works pretty fine. So that size S was chosen for the baseline. Batch size was 16, which was default, and image is 640, which is also a default parameter. And according to the Ultralytics specification, those parameters are the default one and could be created for establishing the baseline. You can also train for the baseline for 300 epochs, but this takes a lot of time. And also the participants can train for bigger number of epochs if they are interested about that. The custom training, the general command, it is here you can use that command, which is using the default parameters. You only have to create your own YAML file with specifying where is the data set. And basically, if you want to start your own solution, you just have to create that YAML file and that's it. And just customizing training is simple example here that you go to your path to the YOLO-V file, number of epochs, data to the YAML file, and weights. You just specify which model you want to train. And here it is linked to that example notebook where we show the solution available for the participant. And this is just like a summary what we wanted to get from that challenge. We want to see if we can implement a different solution, something better, something with more accuracy, and maybe get some brainstorm ideas which we can use in our system, which is currently working. That is the end of my presentation. And if you have any questions, please feel free to ask or drop a line in the chat.
I guess we might be having all the questions later at the end of the session. In that case, we can move on to our next speaker, Joan, who is been most of his life he's been into programming. He's an engineer by profession, and he's also an expert in data science and machine learning. You're on mute.
Yeah. Good morning, everyone. Now you hear me, okay? I will try to share my screen. See if that works. It's not here. Sorry. It's this one.
No, we are not seeing the screen shared. Yes, okay. Now perfect.
Right? Sorry. Okay, here we are. Well, I will explain you a little bit of how, well, the solution that we have implemented, and it's currently running production. We are using it in the Mosquito Alert system now. We call it AIMA. Well, this comes from Artificial Intelligence Mosquito Alert. Well, our system, I will first talk you briefly about the singularities of this system, because it is important to take this into account. First thing, because this makes the challenge more important. No, first is that the kind of images that we receive from the citizens are quite heterogeneous, both in content and the quality of the images and the different zooms. So this is very different from training a neural network based on a training data set that has been prepared in a lab, where people usually takes pictures from different angles, from different perspectives, with different kind of lights. But okay, this is never the same as the images that we receive from citizens, which are really quite different. Also, the other problem that has also commented here by Monika is that we have a really high class imbalancing in the classes that we need to identify. And also another important singularity of this challenge is that it has public health implications, as Frederic and Eritja have explained. We always have to rely at the end on the expert's truth. That means that AI has to be just a tool to help the task of the experts. But I mean that the focus is not on substituting or substituting the task of the experts, but to help them and assess them in performing their task. Okay, but we know that at the end, for the most extreme cases, the experts' ground truth is what will prevail. So the focus is not on species classification per se, no, as by itself, but on saving experts' time. And this consequence of this is that we have here a recall precision trade-off. Because, well, as I will explain, the idea is not to have a high recall, but a high precision classification. No? So in this sense, probably the focus of the solution that we have implemented is different from the way that we have focused the challenge. And well, you will see this as I will go through this talk. This is a scheme about the current solution that we have implemented. So we have here, you see at the left, that our server receives the reports from the citizens. We have received two kinds of reports, basically. Well, we have breeding sites and adult mosquitoes. And we are basically interested in those ones from images with adult mosquitoes. And our system basically is built up of three main filters. Which one is this one, which we call is insect, another one which we call find mosquito or cropper, and another one which we call find species. And I think you are all guessing by now what's the purpose of each one. No, this one just is a first kind of coarse grain filter that selects images that potentially have a mosquito in it. So this filter recognizes everything that might be a mosquito in it, and separates these images from images that do not have mosquitoes, because we receive many images with selfies, or images with bites, or images where of plants or whatever, where there is no mosquito in them. No, so for the sake of saving time to our experts, these kind of images, which we call off-topic images, we we separate them, and it's these negative examples that we send through this part of the system. Okay. Then positive images, that means images that have a potential mosquito in them, are sent to a second filter, which is basically a regional convolutional neural network that finds the area where the mosquito is and defines a bounding box around it, so that we can crop it. And once they are cropped, they are resized to size of 256 we are using currently, 256 by 256. And these images then are analyzed by this third filter, which we call find species, which tries to identify the species. Okay. So these are the three filters. This insect is a binary classifier. It's based on a ResNet 18, and it works quite well. It currently has an accuracy of about 98%. So we are happy with this filter. Then we have this second filter, the cropper, which is a single object detector. It's based on a fast regional convolutional neural network. I know that this will probably sound as a very old algorithm to most of you, but okay, that's the one that we use at the moment when we started this project 2 years ago. But okay, it works also quite well, and we have an accuracy of roughly 96%. And then we have the find species filter. This is a multi-class classifier. It is based on a mobile net, pre-trained. We use transfer learning here, and we fine-tune it with a strategy for layer freezing and unfreezing, because the mobile net V2 is pre-trained on a standard image dataset like ImageNet or CocoNet. I don't remember now exactly. I think it's ImageNet. So it is basically trained to recognize and make an extraction of high-level features that would correspond more to the kind of objects that are represented there in this image dataset. So we found that it was necessary to fine-tune it. We not only replaced the classifier layer, but also we decided that we needed to make this fine-tuning, and we use a strategy in which we were freezing and unfreezing layers, the swallower and well, all the layers of the architecture to achieve better performance. And this filter, we have 8 classes here. You will see a difference from what we have, well, from the challenge. In the challenge, you have 6 classes. In our system, these filter classes, 5 of them correspond to the targeted species of the project, which are cool experience, which one? Japonicus coraicus, which we decided to use the complex class, as Roger explained, because the difficulties in trying to identify each one of these species by separate. And the fifth target, which one is? We have Egypt and Egypti, Albopictus, Japonicus quercus, and well, okay. Well, no, it's 5 because it's Japonicus and quercus, but these are in reality four classes only. Yeah. Then we included 2 classes more because in the near future we devised these classes will be necessary to identify them for the public implications, public health implications that they might have. And these are the Anopheles and Culicetas. And then we included two extra classes more. One which we call other species. That means that from the result of the first filter, the is insect filter, well, this one detects just everything that looks like a mosquito, but does not distinguish, for instance, flies or bees or these kind of things. No, it's a coarse grain filter. So in order also to save time to the experts, so that they do not need to waste time validating a report in which the citizens reported a fly or a bee. So it's good to try to identify these images. So we include all these images here, all these kind of other species in this class. And also another class, which is blurred images, because in blurred images, many times we have kind of stains or blobs that might look like a little mosquito, and they are not. No? So it is important to distinguish also these images that are not filtered by the is insect filter. And with this fine species filter, well, we prepared a training data set that I will explain you, which we call the gold data set, with which we achieve an accuracy of 99% in the identification of these classes. But once this model is implemented in production, and we have to classify images that are much more heterogeneous than those that are in the gold data set, then the accuracy of this filter drops to 70%, with a recall of approximately 50%. And well, why did we do it this way? Well, the motivations for this, for designing the system this way. First one, at that moment, we didn't have a large experience in using deep learning. And so we decided that it was better to break one complex task into simpler ones. And as soon as we start training, we saw that training with taking just the whole data set and using it to train, then the class precision was really low, because the data set is really very noisy. So we have the intuition that we could improve the accuracy by removing noise. That means that we make a selection of images in which the species could be really identified. So the idea was that if we remove all images in which there is noise, then we might be making the model learn the taxonomic features of each species, which is what we really wanted. So the goal was to achieve high precision in the class identification for those images in which the taxonomic features of the mosquitoes were clear enough so that we can identify them with high precision, though that was going, of course, at a cost in recall. But okay, as I told you in the beginning, as we know that the purpose is not to substitute the task completely, substitute the task of the experts. We know that we have to rely on them because this has public implications, public health implications that we have to take into account. So we need experts, however. But what we want to do is to prioritize the attention of the experts to those images that are most difficult to identify. But those that are easy to identify, those ones are the ones that we want to classify with high precision. No? And of course, this is different from the motivations for the challenge, in which the performance of the system, well, in which, sorry. Well, the motivations of the challenge are that, of course, the performance of our system is clearly not optimal, can be improved. That's clear. We are aware of the evolution of a solution in 3 parts. Single detectors traction, accurate each time. So we would like to we can one kind. Bird and other species, because they are still very noisy. What we have there is too variable, and it's not good. So this is why we remove these classes from the challenge, and you don't have them you don't have these classes in the challenge. But we are thinking on future edition in this set of classes, and then we can have a global solution for that can be really applied for Mosquito Alert. And well, that's basically what I wanted to explain you about the current the system as it is implemented now. And I better now leave room for you to that you probably have questions, or you have issues that you have come across when training with our data set. And I would like to hear your opinion about all of it.
Thank you for your presentation. We can move to questions, but before that, I thought that we can just, since we have all the organizers here, just have a short preview of what to expect for round 2. What are some of the changes? And if you have questions pertaining to round 2 phase 2, we can discuss them on this call as well. So I'll just quickly share my screen. And yeah, so here are some of the main updates for phase 2. This phase will be accepting code submissions, and more details on this will be included in the starter kit. The data set for this phase is also improved. So the test data set for round 1 has been integrated into the training data set for round 2. And there's also been changes to the data set. So there were some feedback regarding images with multiple mosquitoes and suboptimal bounding boxes. So we have tried to remove them in the training set, and there might still be 3 to 4% of such images, but overall the quality of the image data set has been improved for the new phase. So that should help training your solutions better. And in case you find such images, feel free to exclude them from your training. Also, regarding the evaluation criteria, it's the same as one from round one, which is employing F1 score, employing a 0.75 IOU threshold, and that's the same. That's unchanged from the previous round. This round will include a private and a public leaderboard, and the final winners will be determined on their position in the private leaderboard. So yeah, so during the live evaluation, only the public leaderboard will be accessible to you. And after the challenge ends, the private leaderboard will also be released with the scores. There were some queries regarding the team formation deadline. Some of you were not able to create a new team. So the team freeze deadline has been pushed to 5th of September. So please make sure that if you want other participants to join your team, if you want to create a new team, it's all done by 5th. You won't be able to create a new team or change your team after that. So I will be adding the starter kit for phase 2 very soon to the challenge page. You'll be able to access it over there, and also send it in the email along with the round 2 announcements. And yeah, that's it from my end. If you have any specific questions regarding the new round or the data set or anything, this is the forum to ask them. Okay, it seems that we all have done such a great job at presenting that they don't have any queries, they don't have any questions. In case they pop up later on, you can always leave them on Discord, email, all the ways to get in touch. And in case I just wanted to have just wanted to invite feedback for the previous round, for the challenge so far. Any critique about Sai, Dinesh, you unmuted yourself. Do you have a question or feedback?
Yeah. Do you have any limit on inference timing of the models that we are submitting here in our phase 2?
I don't know the answer for that, but
Deepa or Mohanty
yeah.
should answer this.
Yes, I think I'll have that query answered in the updates itself. Deepam is currently occupied testing the models for the new phase, so he could not join this call. But I'll check with him and update it on the discourse post. Thanks for flagging that. I'll note it down.
Thank you.
Yeah, so if we have any feedback specific to data set or the challenge structure or any queries or questions, now's the time.
I would have one concerning the bounding boxes. So you mentioned that you've sorted out images with more than one mosquito. Did you also update the bounding boxes themselves, or were they the same as for phase 1?
Yes, we've tried to do it. We have had a hard time doing that, but of course it was not possible to check all the bounding boxes, because at the end, if you want to be sure that they are accurate, all of them, you have to practically visualize all of them, no? And that was really tough. And from these 10,000 images, we have visually checked about 7,000 of them. And in those, we have seen that we have about 3-4% of images with multiple mosquitoes, either with multiple mosquitoes or with suboptimal bounding boxes, let's say, no? And we have been removing all of them. But that means that there are still 3,000 images in between among these 10,000 that have not been revised. So that's why we were pointing out that you can still find some of these images with suboptimal bounding boxes, or even maybe a few images with multiple mosquitoes. But we have done it as well as we have been able. But it's a tough task. So that's why we say, if you find images, well, it is important to note that in the test set that we will be using to evaluate your models, there they have been carefully removed all images with more than one single mosquito and with not accurate bounding boxes. So we will be testing your models with a test set with accurate bounding boxes and where each image contains just one single mosquito. So take this into account, and that's why we say, okay, if you find images in the training data set where you have multiple mosquitoes or you have not accurate enough bounding boxes and you think that they are detrimental for the training of your model, then we decide to remove them. And okay, you're perfectly welcome to do it. Does that answer your question?
Yeah. Thank you so much. And also, yeah, thank you for organizing this challenge. I think it's very well organized. And also thank you for the session today. It was very helpful. And yeah, thank you so much.
All right, so if we don't have any more questions, I think we can conclude this event. Thank you all for staying till the end. I know this went a little above the time limit that we had in mind, but thank you for being around.